All right, so welcome to Dynamic Ensemble-Based Scenarios for IDSS, or DESI training, and this is brought to you by myself and the whole entire DESI team, which is listed down here. So I just wanted to begin with the outline for today's training. So we're going to begin with what is DESI, then we're going to talk about the motivation and sort of the grander vision for DESI. We're going to go over the DESI rollout and test plan. We're also going to go over the technical aspects of DESI, as well as a review of the ensemble clustering method that's employed by DESI. And then finally, we're going to get to the most important part, which would be a DESI live demo. So what is DESI? DESI stands for Dynamic Ensemble-Based Scenarios for IDSS. And it's the NWS's new prototype platform for the effective visualization and incorporation of ensemble forecast information into the forecast and IDSS process. So the website address for DESI is down below. You do need a password or WPC specific password to access it. And that information was emailed out by Mark Klein at the beginning of the month. So if you are interested in using DESI, please go see that email for the username and password. So what's the motivation behind DESI? So basically, the NWS has been lacking tools for the effective visualization and incorporation of ensemble forecast information. And this obviously creates problems for a forecast process that is increasingly relying on ensembles. So many forecasters frequently choose to consult third-party websites, so for example, WeatherBell, to effectively visualize ensemble forecast data because the NWS doesn't really have anything comparable. So there has been work to kind of rectify this. So from 2018 to 2020, WSUP and the NBM 1D Viewer were developed to help forecasters better understand and visualize NBM forecast data. At the same time, WPC developed ensemble clustering products to assist forecasters in processing, synthesizing, and visualizing ensemble data. So basically, the NWS has the people, the technology, and the infrastructure to create an in-house web-based platform for the effective use and visualization of ensemble forecast data. So why shouldn't we go about doing that? And this platform should allow forecasters to dig more into the data like can be done on third-party visualizations, but it should also integrate powerful information synthesizing techniques, for example, ensemble clustering and NWS value-added data sets. So for example, the NBM bias-corrected data that are not offered by third-party platforms. So in 2021, a team of people, including myself, from across the NWS was formed to create such a platform. So what's the grand vision for DESI? Well, obviously, as we all know, the NWS wants to reduce the amount of time forecasters spend manually editing grids and increase the time spent understanding and communicating the forecast and its uncertainty to core partners, otherwise known as IDSS. So DESI will be a platform to better understand the forecast and its uncertainty, as well as plausible alternative forecast scenarios through statistical and ensemble cluster analysis. DESI will ultimately be driven by the NBM bias-corrected membership, but for now it is driven by the raw global ensembles, which consist of the Canadian ensemble, the GEFS, and the European ensemble. So ultimately we want it to be driven by that NBM data, but for now, this first prototype is more of a proof of concept that's just using the ensemble data that we have available to us at the moment. So what's the DESI rollout timeline? So obviously July of 2022 was the initial prototype DESI rollout, which was rolled out to 40 WFOs and 1 national center, which was WPC. From the summer of 2022 to the fall of 2022 will be the initial testing of DESI. So basically we want people in those WFOs and at WPC to use it, give us your feedback, tell us what you like, what you don't like, what you wish it had, because STI basically has, DESI has the full support of the STI, and it's going to be around for a while. So this is your opportunity to kind of shape the future development of DESI and make sure it's something that you want to use and something that works for you. So from the winter of 2022 to the spring of 2023, we will be implementing any enhancements that are ready to go, and also leveraging the operations proving ground to further test DESI. From the spring of 2023 to the summer of 2023, we will be adding further enhancements to DESI. And then finally, we are targeting the summer of 2023 for a rollout of DESI NWS-wide. So some of the technical aspects of DESI. So what are the ensemble data sets that's included? Well, for now, it's just the half-degree resolution versions of the global ensembles. So again, the Canadian, the GEFS, and the European ensemble. How often does it update? It updates twice a day. The 0Z ensembles are available at approximately 11Z, and the 12Z ensembles are available for viewing at approximately 23Z. So what sort of data is available? Well, there's meteograms, and they're available at any location, and you can view chiclet charts, plumes, histograms, and box plots. And I have a little example of that on the right, but we'll go over this all in more detail when we do the live demo. There's also 2D plots, which are available with customizable features. For example, you can zoom in and out. You can toggle on and off WFO boundaries or RFC boundaries, and a few other options. And I have an example of one of those plan charts right here. So what is the statistical analysis that's available? Well, you can view percentiles, maximum values, minimum values, interquartile ranges, and differences from the multi-model ensemble mean for each ensemble system independently or any combination of those systems. And as for the ensemble cluster analysis, it will be the new home for WPC's ensemble clustering products. So now I just want to go over the ensemble clustering review of the method, as that's the part of DESI that I've been most involved with. So basically, the motivation for ensemble clustering is that the national blend of models is increasingly being used as a starting point for NWS forecasts. Obviously, we all know that. And the NBM does a good job of blending a large volume of forecast data into an accurate and actionable forecast, but it's kind of a black box. And forecasters want more information on what went into the NBM, as well as information on forecast uncertainty in space and time that the NBM doesn't necessarily provide. And they need tools that will give them this information. So one solution, although an impractical one, would be to view all of the ensemble members. But obviously, if you're looking at a multi-model ensemble system that has 100 ensemble members, that's too much information to take in a short amount of time. And even if you have the time to look at all 100 ensemble members, it's kind of hard to remember, what were the overarching themes between those various 100 members. An overly simple solution would be to calculate the ensemble mean for each EPS and treat it as the possible forecast scenarios, which is what has traditionally been done in operations in the past. So the benefits of this are that it's simple and lets forecasters somewhat see some of the underlying data that went into the NBM, but the drawbacks are it doesn't adequately show the range of possible forecast outcomes, and it assumes that the biggest determinant of an ensemble member's forecast is its parent model, which is not a valid assumption. So the better solution is ensemble clustering, because ensemble clustering will partition the members of an ensemble into groups of members that have broadly similar forecasts, or in other words, discrete forecast scenarios. By simplifying the ensemble down into a few clusters, it allows forecasters to dig more into the data without getting that data overload. So to assist forecasters in the creation of medium range or day 3 to 7 forecasts, WPC developed an ensemble clustering tool, and then DESI will be the new home for this tool. All right, so ensemble clustering, how to cluster. So DESI uses a version of clustering known as fuzzy clustering, and basically fuzzy clustering has a 3-step recipe. First step is to evaluate and interpret the first 2 empirical orthogonal functions, or EOF, of a relevant ensemble variable over a region of interest. The second step is to use k-means clustering on the principal components, or PCs, for the EOFs to create clusters of members with similar forecasts. And finally, the most important step is to view the clusters. So the specifics of DESI's fuzzy clustering method. So what are the ensemble data sets used? Again, it's the half-degree resolution version of the global ensembles, which are the Canadian, the GEFS, and the European ensemble. As I've said earlier, we ultimately want this to be driven by the NBM bias corrected data set, but for the time being, we don't have access to that, so we're just using the ensemble data that we do have access to. The relevant variable for EOF analysis is 500 millibar Heights, and we've chosen that because it's a good summary variable that can kind of show you where the areas of above normal and below normal temperatures are, as well as the approximate location of the storm track where any heavy precipitation might be focusing. The regions of interest will be several larger domains over the CONUS, for example, the East, Central, and West, and as also several smaller regional domains, for example, the Pacific Northwest. So how many clusters are appropriate? So generally 2 to 5 clusters is appropriate, but what we do is run k-means clustering on the EOF PCs with 2, 3, 4, and 5 clusters, and then we use what's called the silhouette score to determine which of these is the optimal number of clusters. So for example, we are going to apply fuzzy clustering to a 6-day forecast over the Western United States. So the first step is to calculate and interpret the first two EOFs. So for those who may be unfamiliar, what are EOFs? Well, they're basically a data analysis technique often used in climate studies as a method for determining the spatial patterns that most efficiently explain the variability of a multivariate data set. So in other words, what patterns are most common in the data set? And it's how we get teleconnections like the NAO, which is just the first EOF of sea level pressure over the North Atlantic during winter. So EOFs that are calculated across the model ensemble member dimension instead of this more traditional time dimension result in modes that show the dominant patterns of differences between individual ensemble members and the ensemble mean. So for each EOF, each ensemble member will have a principal component. So what are principal components? Well, principal components are the projections of the dominant EOF patterns onto the difference between each of the ensemble members and the ensemble mean. So basically, the English translation is that an ensemble member with a large PC for a given EOF pattern will resemble the ensemble mean with that EOF pattern added or subtracted to it. And whether you add or subtract depends on the sign of the principal component. So it's a lot of math, but you don't need to know the math in order to interpret and imply the results of the EOF analysis. So to illustrate that, we're going to be calculating the EOFs of 500 millibar height over the Western US on day 6, which we have defined as 0Z on the 23rd of May to 0Z on the 24th of May from the global ensembles that were initialized at 0Z on the 18th of May. So these are the first two EOFs. On the left, we have EOF1, which explains about 54% of the variance. And on the right, we have EOF2, which explains 25% of the variance. In both of these two panels, what's contoured is the multi-model ensemble mean, and then the shading is the actual EOF pattern. So we can see a trough kind of over the Intermountain West with ridging building in over the west coast of the United States. This first EOF pattern is a monopole that's kind of located between the trough and the ridge couplet. So when we have a monopole like this that's kind of located between two features, what this is telling us is that there's differences in the timing. So in this case, EOF1 represents how fast that trough will pull out and how quickly that ridge will build in. Looking at EOF2, we can see that it shows some lower values off the coast of the Pacific Northwest. So in this particular case, this EOF2 is saying that the other area of uncertainty in this forecast is how much ridging there will be off the coast of the Pacific Northwest. All right, so then, as I said, each ensemble member will have a principal component that relates it to that particular EOF. So what you can do is you can construct a phase space, and that's what we've done here with the principal components for EOF1 along the x-axis and the principal components for EOF2 on the y-axis. And then all of the ensemble members are plotted in this PC1, PC2 framework. All right, so all the members that are in this part of the phase space have principal components for EOF1 that are positive. So essentially, you would be adding this pattern here to the multi-model ensemble mean. So you have the effect of lowering the heights over kind of like the Las Vegas area. So in other words, the members that are in this part of the phase space, they represent those members that have that trough, hanging on a little bit longer. If you go to the left part of the phase space here, these are the members that have principal components for EOF2 that's negative. So essentially, you would be subtracting these lower heights, which has the effect of raising them over the same area. So these are the ensemble members that have, that ridge building in faster. And you can perform the same sort of thinking with EOF2. So in this case, all the ensemble members up here have a positive principal components for EOF2. So you're lowering heights off the coast of the Pacific Northwest. So less ridging over the Pacific Northwest is what this part of the phase space denotes. And then down here in this part of the phase space, you're basically subtracting lower heights. So in other words, raising them. And you have more ridging over the Northwest in that part of the phase space. All right, so then the next step is to use k-means clustering on this phase space. So what is k-means clustering? It's an algorithm that groups two-dimensional data to minimize distance between each point and the center of the cluster it's assigned to. So the number of clusters needs to be specified beforehand. And as I've said, 2 to 5 is usually appropriate. So to select the optimal number of clusters, what we do is rerun our k-means clustering on the EOF PCs to create 2, 3, 4, and 5 clusters. And then we just select the number of clusters that resulted in the highest silhouette score. And the silhouette score is just a measure of how similar an object is to its own cluster versus the other clusters. And in general, a higher score is a better score. All right, so now we've gone through and we've clustered all of the ensemble members using our k-means clustering algorithm, and we have 3 clusters. So if we look at cluster 1, those are the ensemble members here denoted by all the 1s. They're down in this part of the phase space. So what they all have in common is they have that principal component for EOF2 that is negative. So the physical interpretation for cluster 1 is that there's more ridging over the northwest. And on the left here, we kind of have each cluster mean as well as how it differentiates from the ensemble mean. And you can see that indeed, this cluster is members that have more ridging off the coast of the Pacific Northwest. Doing the same sort of thinking for cluster 2, that represents the trough hanging on longer with less ridging over the northwest. And then finally, applying the same sort of thinking to cluster 3, the physical interpretation for cluster 3 is that ridge builds in faster, but less ridging over the Pacific Northwest. And the relative support for each ensemble or for each cluster is kind of given at the top here. So for example, this cluster 1 has 13% of the guest members, 61% of the European members, 30% of the Canadian members, for a total of 41 members or 41% of our 100-member multi-model ensemble. So that's how we derive the clusters, but really you don't need to look at that information to understand and physically use the clusters. You could just go to the cluster output and everything will be pretty much apparent there. So on the left here, we have the 500 millibar heights for each cluster 1, 2, 3, as well as the multi-model ensemble mean. And the shading shows the difference between that cluster and the mean. So again, you can clearly see the physical interpretation of each cluster, with cluster 1 being more ridging over the northwest, cluster 2 being more troughing, and maybe west, but not as much ridging over the northwest. And then what we do is we can look at based off these 500 millibar height clusters, we can look at other variables and see how they shake out based on differences in the large scale pattern. So what we have here is the 2-meter temperature differences for each of the clusters. And if you kind of just relate it back to the 500 millibar heights, it makes sense. So for example, let's look at cluster 3, which had higher heights over the southwest. No surprise, cluster 3 has warmer temperatures over the southwest and cooler temperatures over the Pacific Northwest. So that's basically a quick overview of the clustering methodology. One thing I wanted to touch on before we move into the live DESI demo is some verification. So over the past couple of years, we've done a lot of work with the clustering methodology, but we hadn't really done a lot of verification. So one of the things we wanted to look at is, does the best performing cluster consistently outperform the best performing ensemble mean or deterministic forecast? So what we did is we used paired verification, and we compared the best performing cluster for each day to the best performing ensemble mean and deterministic model. And we did this over a period of 6 months, and the results of which are kind of shown in this bar chart here. With the best cluster being shown in the blue, the best ensemble being shown in the yellow, and the best deterministic in the green. So what we're using for verification is the mean absolute error for the 500 millibar heights. And we can see that for days 3 through 7, this best cluster, which is is denoted by the blue here, does have lower error than the best ensemble or the best deterministic. And these error bars here are just kind of here to signify that these results are 95% significant. So basically the take-home message here is that yes, indeed, the best cluster does outperform the best ensemble or deterministic model. But another take-home message from this chart is that, earlier in the period, say day 3, while the difference is statistically significant, there's not a large difference. But as we go out in time, the advantage of using the clusters really increases, so that by day 7, the best cluster is, pretty substantially outperforming the best ensemble mean or the best deterministic model. So basically what we're trying to impress upon people is that, clustering can be useful throughout the day 3 to 7 time period, but the value really comes in later in the period when that forecast variance increases. So a summary of the clustering method. So the EOFs show the dominant modes of uncertainty in the forecast. Ensemble clustering uses the EOFs, and it does a good job of showing the alternative forecast scenarios to the most likely scenario. Using the silhouette score, to allow the number of clusters to vary. So that's how we determine the number of clusters. And then clustering will be available for days 1 through 9. But with that said, if spread in the forecast is low, so in other words, clustering won't be helpful, DESI will only return one cluster, which is the multi-model ensemble mean. And this is very common on days 1 and 2. So for future work with DESI, one of the main things we want to do is, as I've said, attain and incorporate the NBM bias-corrected membership, because obviously having this half-degree data, it's nice, it's useful, but it doesn't really capture a lot of the higher resolution features that we're interested in forecasting for. Another thing we want to do is enhance the ensemble clustering methodology. We would like to expand to other ensemble data sets, for example, the href, and also add any user-requested features that are feasible. So to submit any feedback for DESI, we have this Google form here. I have the link here, but also when we go and do the live demo, there's going to be, I'll show you where it's linked on that page as well. So you don't have to remember this link. But that's basically the form we're using to kind of elicit feedback that will impact the future development of DESI. Also, you could contact the DESI support team. We have an email. It's desi.support@noaa.gov. And also we have a VLab page with some more training if you would like to go there and look at that later on your own time. So with that, I think I will pause here. And does anyone have any questions before we go into the live DESI demo portion? Is there a hand up?
Yeah, hi there, Bill. Yeah, this is Mike Schichtel. Yeah, a question I have for you is when you say the best ensemble, how does that differ perhaps from the verification from the ensemble with the most ensemble members verification?
So you're asking, like, how does that compare? So you're saying, you know, like comparing to the European, which has the most members, or just?
No, the cluster with the most members, I'm sorry.
Ensemble members. We didn't separate out, and that's a good question. That's maybe something we can look at in the future. But yeah, so for that verification, we were just looking at the best performing cluster overall, regardless of, you know, the size of it. But yes, that's something we could look at in the future. Are there any other questions? All right, then I will move over to the live demo portion. All right, so this is DESI, obviously the website, desi.noaa.gov. So if you go there, this is what you'll be confronted with. We're just going to start by going over this left panel here. Basically, it starts with the forecast run, so obviously it's going to default to the most recent one. But you can go back and look at the past couple of weeks of forecasts if you would like to, but we'll just stick with the most recent run for now. There's the option to switch between different data sets. So what we have what's called the LREF, which we're just, you know, it's just the nickname for the low resolution ensemble forecast. So it's just our nickname for the combination of the half-degree GEFs, Canadian and European ensembles. So we have data for the CONUS, but if you wanted, you could look at data for Alaska or Hawaii. Obviously, for OCONUS concerns, we wanted to be inclusive of them. But we'll just stick to the CONUS for now. As you've probably surmised, DESI is quite flexible in terms of the area that you're going to look at. So you can move this all around. You can zoom in, you can zoom out. I'll just quickly go over some of the other features. If you click on this Maps button here, so right now we have the countries, the state lines, and the cities selected. But if you wanted, you could click County Warning Areas and turn those on, turn those off, RFCs, turn those on and off. And then down here, this panel here is how we animate DESI. Obviously, you can just use your arrows, which I'm going to do right now. Or you can drag this bar here and it will animate the forecast in time. So again, this is the half-degree ensemble data, so we only have 6-hour chunks, basically. You could animate it by clicking the forward or backward button, or even if you wanted to, you can have it play an animation for you by clicking on this play pause button, which I'll do right now. And to speed up or slow down the animation, you can use these two buttons right here. So if you wanted to speed animation, you can, or you can slow it down. So that's a little bit of the knobology of DESI. So now we're going to go back over to this side panel here. So it defaults to viewing the Canadian ensemble. So that's what we're looking at right now. We're looking at 2-meter temperature from the Canadian ensemble, and we're looking at the ensemble mean. But if you want, you could look at the European ensemble. You could look at the Gefs ensemble, or you could look at a grand ensemble, which is a collection of all 3 of those ensemble prediction systems. Then over here is where you can look at some of the different percentiles. So again, it defaults to the mean, but if I wanted to, I could look at the 90th percentile. And this is all calculated on the fly, so sometimes it takes a second or 2 to load. But there's the 90th percentile, or you could look at the max from that 100-member ensemble. But let's just go back to the mean for now. So as I said, it defaults to the 2-meter temperatures, but there are other parameters. If you click on here, you can look at some upper level variables, for example, 500 millibar heights, and then there's some collections with multiple variables, so 500 millibar temperatures and heights. We also have some precipitation variables, so for example, 6-hour precipitation, 24-hour precipitation, total precipitation. We have one convection parameter, CAPE, several surface parameters, including 2-meter temperatures, sea level pressure, wind, relative humidity, and cloud cover. Now, obviously, to start off, since this is just sort of our first prototype, there's not, every variable that you could think of. It's just a small collection of variables, because as this is more of just a proof of concept. But those are the variables that are available. So let's just quickly look at 500 millibar heights. And as you'll see, for a lot of these, there are statistics and ranges. So if you click statistics, that's where you can kind of look at the various different percentiles. So right now we're looking at the mean 500 millibar height. But again, we could just look at, say, the 90th percentile. Just go back to the mean. And then if you click ranges, this will give you some idea of kind of the forecast uncertainty or spread. So now you can choose between either the 90th minus the 10th percentile or the 75th minus the 25th percentile. So let's just take a look at that. And as we kind of step through, we can see obviously there's no shading because at least at the beginning of the forecast, there's not a lot of uncertainty. But as we get further into the uncertainty or further into the forecast, we can see that uncertainty is increasing with this trough feature that's moving into the Pacific Northwest, which we'll kind of be using to explore some of DESI's ensemble clustering aspects later. But let's quickly just go back to the statistics for a second, because I want to cover some of these other features. So right now, we're looking at the grand ensemble. If we wanted to look at all 3 ensemble prediction systems as well as the grand ensemble, we can do that by clicking this panel button here. So again, it takes a second to load, but now we're looking at the Gefs ensemble, the European ensemble, the Canadian ensemble, as well as the grand ensemble. Now, obviously, looking at a plot like this where value you're looking at is what's shaded and contoured, it's very difficult to see some of the differences between the various ensembles. So if you would like to see the differences, you can do that as well. And that's to do that, you click on this button here, which will create differences from the grand ensemble. So again, you can kind of toggle back and forth quickly, or just keep it on one. And same thing with the paneling. You can easily toggle back and forth between looking at all 3 ensembles to, say, just looking at the grand ensemble, which is the collection of all 3 of those ensemble prediction systems. If you wanted to, there's this other thing which will swap what's being shaded and what's being contoured. So obviously that wouldn't really make sense since 500 millibar heights is both contoured and shaded here. But if we look at the differences again, right now, the 500 millibar heights are being contoured with the differences shaded. But if we flip this, now the 500 millibar heights are shaded and the differences are what's contoured. I mean, personally, I like looking at it this way. But if you wanted to, you could look at it another way. And then also you could take a screenshot of the data as well. So that's sort of an overview of kind of the 2D plots in DESI. Another interesting thing you can look at, and kind of what I've advertised, is the mediogram plots. So to get to that, you would click over here on this sort of bar chart thing. So right now we're in 2D plan view, but we can quickly switch over to the mediogram view. Now it defaults to the METAR location for Spokane, and that's because one of the developers was the Sioux at Spokane, but you can enter in any station you would like. So for example, we can just add, let's do Dulles, and it'll quickly regenerate the mediogram stuff for Dulles. But let's actually, well, and another thing I should mention is it doesn't have to be a specific location, like station location as well. You can just move this around and put it anywhere. So for example, you know, there's been a lot of issues with the flooding in Tennessee. If I wanted to look at, say, precipitation there, I could just plop it there and it'll interpolate to the nearest grid point. So it doesn't necessarily have to be a station location. But let's just go back to Spokane because the forecast, at least in the medium range, is looking a little interesting there. So, and obviously, this is sort of the default view, which is an overview, which has a lot of data, a lot of different variables, which can be a little bit overwhelming to look at. So what I like to do is actually look at each variable kind of individually. So let's just click on that button. And it defaults to precipitation, but let's take a look at like 500 millibar heights quickly. So what you get is a chiclet chart, and then down here is a histogram, which will kind of change as you scroll through the forecast. So, you know, at the beginning of the forecast, obviously there isn't much spread. The histogram is pretty, you know, tight and confined. But as we go out into the forecast, we can really see that the uncertainty, especially as we get into like Monday and Tuesday, is really increasing. We can see a much wider histogram for the range of 500 millibar height values. So if you don't like histograms, you could also look at whiskers. You could look at plumes to show the mean of each ensemble system, or you could look at plumes which show the values for each of the ensemble members, which obviously is a little bit busy, but some people might want to look at that. If we go over here, obviously we've still been in this ensemble view the whole time, and we will get to the cluster view, but for now we're going to stick in this ensemble view. If we get down here, obviously as I'm sort of mousing over each ensemble prediction system, it's highlighting the members that are associated with that ensemble prediction system. If you wanted to keep them highlighted while you go about doing something else, you can click that and it will keep them highlighted while you go look at maybe some other query, some data by looking at the chiclet chart here. So you can turn that back off. And also you can look at any combination of these ensemble prediction systems. So for example, maybe I just wanted to look at the guess values and I didn't really want to look at the Canadian or the European ensemble. I can just turn them off and everything will rejigger itself so that you're just looking at the guess ensemble members. So let's turn them back on. And then obviously down here, there's this DESI survey button. That's how you get to that Google Docs where we are eliciting survey information. So that's basically sort of the mediograms overview. So let's maybe look at maximum temperatures. So as I said, you know, as you sort of I like looking at the histograms personally, so I'm going to go back to the histograms. So as we get kind of further into the period, and especially on Monday, we can see there's kind of a lot of uncertainty in the maximum temperature forecast for Spokane. And actually, if we look at this histogram, it's kind of multimodal with, you know, some ensemble members in the mid 80s and another group that's more in the mid 90s. The ensemble mean, which probably, you know, falls in the middle here, has less support. So this could be a good case to look at for some of the ensemble clustering products we have. So let's go look at DESI in the ensemble clustering mode. So I'm just going to go to this tab here. So I could have gone from this tab and just click the cluster and it will take me to the cluster portion of this, but I'm just going to go to a new tab. Again, this is where you would start out if you just came to DESI for the first time. And now I'm going to click into the ensemble cluster mode. So basically it's gonna, I think it usually defaults to the west, but for right now, we're gonna look at the northwest, and we're interested in the uncertainty on day 5. So we're gonna pick day 5 as our clustering period. So what you can see is in this particular case, we got 5 clusters. They'll be displayed here. And the shading in each of these sort of panels right here shows the difference from the multi-ensemble mean for the 500 millibar heights. And then this red box is just kind of highlighting the area over the domain over which the EOF and cluster analysis is conducted. So this is just kind of a summary to let you know how many clusters there are and the relative support, but you can just make that disappear if you want to see some of the data more closely. So let's just look at, say, the 500 millibar heights. Again, we'll go to the statistics. Let's do the multi-panel because I want to see all 5 clusters as well as the multi-model ensemble mean. Again, it takes a little bit to load because it does all this on the fly. All right. And I want to look at, the difference from the multi-model ensemble mean because it's really hard to see, how those forecast scenarios are different if you're just looking at the actual raw parameter. And if you're in cluster mode, you'll be limited just to the day you're looking at. So there's only going to be instead of starting at the beginning, and showing all 240 forecast hours, it's just going to show the forecast hours that are associated with that particular day. And you can clearly see how there are differences in the forecast. We can see cluster 1 and cluster 4 are going for more ridging over the Pacific Northwest, whereas clusters 2 and cluster 5 are going for more troughing over the Pacific Northwest, and cluster 3 is sort of in the middle and kind of hews pretty close to the grand ensemble there. So that is the upper level heights. So again, if you wanted to look at, say, temperatures, so let's go to 2-meter temperatures. You can see differences as well. And no surprise, cluster 1 and cluster 4, which had more ridging over this area, are going warmer. And as you're scrolling over it, it actually shows you how much warmer. You can see that in that little pop-up there next to the cursor. Cluster 2, no surprise, were the 2 clusters that had more troughing over the Pacific Northwest, and they're cooler. Whereas cluster 3, which wasn't that different from the multi-model ensemble as opposed to the 500 millibar heights, and it's not that different for the 2-meter temperatures. So that's sort of the plan view in cluster mode, but you can also look at the meteogram plots in the cluster mode as well. So that's what I'm going to go to by clicking this button here. So again, it takes a little bit to load, but let's just kind of minimize that for now. And maybe we'll look at maximum temperatures because again, that's, it's an interesting forecast with that multimodal distribution there. So if we just select the maximum temperatures, again, the period of clustering will be highlighted. And again, we can see that multimodal mean down here in the histogram. But now if we wanted to look at the plumes, we'll get the mean of the clusters as opposed to the mean of the multimodal ensembles. And this kind of really illustrates, we have cluster 1 and cluster 4 and cluster 2 and cluster 5 are kind of, radically different, with cluster 3 being sort of in the middle, closer to the mean. But in this particular case, the mean has less support. So I think, for this particular forecast, that's something you would want to be aware of. As if we just kind of quickly expand this, we can see that, again, the warmer clusters were cluster 1 and cluster 4, which combined for about 40% of the ensemble members, and cluster 2 and cluster 5 combined for about 35% of the ensemble. So in this case, that ensemble mean scenario doesn't have a ton of support, and that would be interesting information to know if you're a forecaster making a forecast for this region. As with the ensemble version of DESI, you can deselect the different clusters if you wanted to. Like, say you didn't want to look at cluster 1, you could just deselect that, and that will go away, and everything will sort of rejigger itself to exclude that. but let's just turn cluster 1 back on. And again, this is the same variables that were available in the ensemble view are available in the cluster view. So we're looking at maximum temperatures, but you could look at any of these variables. So let's just click on 500 millibar heights just for an example. And again, you can sort of see that multimodal distribution is being picked out when we look at the clusters. We have 2 clusters that are much warmer than the mean and 2 clusters that are much, much lower heights than the mean. So that's basically an overview of DESI and sort of, a live demo of all the features and capabilities. Does anyone have any questions? All right, yeah, if someone raised their hand, just, shout out. I can't really see who raised their hand, so.
Hey, Bill, it's summertime right now. Are the winter elements, are they turned off, such as snow accumulation, ice accumulation, or are those a part of the system?
Right now, those are not variables that we have as part of the system. Basically, when we transition to using the bias-corrected data from the MBM, we would like whatever data they can give us. And if they can give us that, that's eventually going to be incorporated. But for now, since we're just using the raw ensemble data, and not all the raw ensemble data, have snowfall. Some of them have, liquid equivalent as snowfall. And I think some of the ensemble prediction systems we get, they don't actually give us the snowfall for each ensemble member. So for now, unfortunately, it's not included. And it's not just because it's summer, but it's something we would be looking to include once we get our hands on that MBM data set.
Okay, thank you.
Hey, Bill, when do the models typically update? Like, when will the 12Z cycle come in today?
So the 12Z cycle will be available around 23Z. So it takes a little while to kind of process all the data and get it in the right format to be displayed in the display here. So it's a little bit more delayed than you could probably see it in like NA-WIPS or something.
Okay, thanks.
Bill, another question. Looked like the clustering options were 0Z to 0Z. Is it possible to have an option of 12Z to 12Z?
That is something we're looking into. And again, if that's something you want to see, we would encourage you to submit that as feedback through, either emailing us at desi.support or going to this DESI survey here. Because yes, we're looking to improve the clustering method, and obviously we know that some events don't fall neatly into that 0Z to 0Z timeframe. So that's something that we're looking into. And if you would like to see that, again, the best way to ensure that that would happen would be to give us that feedback. Any other questions? All right, then if not, I guess we will conclude the training and I will stop the recording. But thank you everyone for coming today. I know it's been a busy day and busy past few days with the weather, so I appreciate you taking your time out and coming to learn about DESI.